So proposition is that every square matrix A of order n. First part of this proposition is has n real complex eigenvalues, real or complex eigenvalues, because when we solve the equation for lambda, obviously we can get real or either complex form. Okay, so depending on the real elements of the matrix A. And next part is the eigenvalues lambda 1, lambda 2 up to lambda n are the n solution for lambda of nth degree. I'll explain you by using example, okay? And so the polynomial equation, that is determinant of lambda into I minus a, can be represented as with real coefficient, and here with real coefficient alpha s, and here s is equal to 0 1 2 up to n minus 1, depending on real coefficient real elements of like this matrix A. And the third point is the possible complex eigenvalues are always pairwise conjugate. Why it is, I'm going to explain you. Means first of all, why we have n values here. Okay, let us understand this proposition by using with examples also. So here, according to order of matrix, we'll have number of values of lambda. How? Because we form this polynomial equation, or you can say characteristic equation, as like if we have square matrix of 3 by 3 order, and E31 means element of third row and first column. Uh, you know, uh, you know these elements because they this is the element of first row and first column, first row and second
Yeah.
column, first row and third column. So we
Yes.
write them according to a number of rows and column. So this is a square matrix of order 3. So when we find corresponding eigenvalues, then we need to construct this equation like A minus lambda into I is equal to 0 by taking determinant, or you can take as also, or lambda into I minus a, I mean, determinant of lambda into I minus a is equal to 0. So obviously we need to take a square identity matrix of the same order, right? And they'll obviously we'll get the three values of that.
Mhm.
Are you getting this point?
Yes.
And similarly, why this complex roots in pair? Because when we find like square root of any, I mean roots of any quadratic equation, so obviously by using the quadratic formula we have in this pair by using plus minus sign. So obviously if we have a complex root, then always we pair.
Mhm.
Okay, by having the positive and negative sign together. Are you getting this point?
Yes.
And this is the third point and first point we have done, because as many as elements we have in diagonal of any matrix, so obviously according to order, it will have the number of elements in diagonal, and according to number of elements in diagonal, obviously we'll find the corresponding eigenvalues. That is why they will be same equal to the order of the square matrix. You got this point?
So okay, so basically we're saying that depending on the number of elements in the diagonal,
Yes.
that is also the number of
The,
eigenvectors that we get.
yes, yeah, eigenvalues according. So obviously the number of elements in diagonal obviously will equal to the order. If we
Hmm.
have 3 by 3, obviously we'll have 3. If we have 2 by 2, obviously we'll have 2. Okay,
Yeah.
that is why the number of eigenvalues will always equal to the order of that square matrix. Now got this point?
Yes, ma'am.
First point of proposition.
Yeah.
Are you getting?
Yes.
Okay. And second point, they are saying that the eigenvalues lambda 1, lambda 2, and up to lambda n are the n solution for lambda of nth degree. Obviously, because we have number of solution as we have maximum power of variable. So here maximum means your greatest power of lambda will be obviously n, because we are taking here n order. So obviously number of solution will be according to that power,
Hmm.
highest power, as we have n, then we have n solution.
Yeah.
Means now got it?
Yes.
Yeah. And third point,
Is this?
obviously, you'll get the eigenvalues, means complex eigenvalues are always in pairwise, where
Mhm.
having the both sign, positive, negative together.
I didn't understand this point.
Pardon?
I didn't understand this point.
Okay, okay. Third point, I'm telling you. Third point, they are saying that the possible complex eigenvalues be always pairwise. Why? Pairwise, let us understand. Like if we have means polynomial equation in lambda, like if we have lambda square plus lambda plus 1 is equal to 0. Okay, and we need to find roots of this equation. So obviously lambda is equal to minus 1 plus minus b square, means 1 square minus 4 into a into c, and over 2 into 1. Are you getting this quadratic formula?
Yes, ma'am.
So obviously here we have minus root 3. So obviously we'll get in pair always, because having this
Okay.
both
Okay.
sign together, that is why.
Mhm. Okay.
Okay.
Understood.
So when we have complex, so means the roots, or you can say complex values of the lambda, then will always be in pair.
Mm-hmm.
Okay.
Yeah.
Because of this.
Yes. Understood.
So here root 3 and into lambda, sorry, iota over 2. So in this way, we can understand that we have complex eigenvalues are always pairwise. Okay.
Yeah. Understood.
Next, remarks on above result equation. Above equation, you can say polynomial means determinant of lambda I minus a is equal to 0 is called characteristic equation of A, and A is matrix. The polynomial Pn lambda is equal to determinant of lambda minus. So lambda I minus A is called characteristic polynomial of A. When this form, when we are using expression in lambda, then it is called characteristic equation, or you can say characteristic polynomial of A. Are you getting this point?
Uh.
Okay,
Mm,
I'm telling you. Okay, just a second. Like if we have equation in this form, so this is called characteristic equation of A, for which we are finding lambda. Okay, or you can say characteristic polynomial also. This part only. See, this part means this equation is equation. I'm telling you on next page also. If you have equation after taking a determinant
mm-hmm.
of lambda into I minus A. For example, we have this equation lambda square plus 2 lambda plus 3 is
Oh,
equal
okay,
to
okay.
0.
So it
So
means
this
that if
equation is called, yeah,
if the matrix if determinant of the matrix of this equation is equal to 0, that means that this particular equation is a characteristic equation.
yes. And this
Okay.
left hand part is called polynomial, characteristic polynomial, this left hand
Mhm.
of this equation.
All right.
This part is called characteristic polynomial.
Okay.
Got it? And this is called characteristic equation.
Okay.
Equation, and this is characteristic polynomial. Okay? So, so now spectrum of A is the set containing all the n eigenvalues of A. Means this is a set of all eigenvalues of A, and
Mhm.
the spectrum of A can be expressed as SA in the form of set having the all values of lambda. Okay,
Mhm.
so shall we do this example?
Yeah.
Okay, all right. So we have here A is equal to 3201. Okay. So here, see, as I told you, I2 represent 2 by 2 matrix, identity matrix of 2 by 2, and I3 represent 3 by 3 order, means identity matrix of 3 order, you can see. Or simply you can use I also instead of them, but sometimes they give you like I2, means we need to take second order identity matrix. Similarly, third order identity matrix. Got it? So here they are using I2 that represent we need to take this one.
Yeah.
Okay? Because we take identity matrix according to order of A. Okay, that is why we are
Mhm.
taking of 2 by 2.
Yeah. Yes.
So now let us understand this. So to find eigenvalues, step one, first of all, we need to find that characteristic polynomial first. Okay,
Mhm.
and how can we find? By using determinant of lambda into I minus a. To find eigenvalues, put or you can take this characteristic equation as. So we need to find this one first. After that, we'll find the determinant of that. So lambda into I minus A. Let us find it. So lambda and take this identity matrix of the same order of as A. And we have A 3, 2, 0, 1. Now let's multiply this lambda inside. We have this result. And now let us subtract A from lambda into I.
Mhm.
So lambda into I minus A, we have lambda minus 3 and 2, 0 and lambda minus 1. Now let us find the characteristic equation by using this. This by taking determinant of this lambda into I minus A. So now let us find it. Determinant of lambda into I minus A is equal to 0 we need to take to find eigenvalues. So let us find now determinant of this lambda I minus A. This is lambda minus 3, 2. 0. Lambda minus 1 is equal to 0. Now we need to multiply these both elements, then take minus sign, then just multiply these. So let us do it. Lambda minus 3 into lambda minus 1 minus 0 into 2 gives means we have 0 right side to form equation. Now let us multiply these two brackets. So lambda square minus lambda minus 3 lambda plus 3 minus 0 or is equal to 0. Are you getting this step?
Yes.
So lambda square minus 4 lambda plus 3 is equal to 0. Now solve for lambda. You can use quadratic formula or you can find by using splitting by middle term.
Yeah. So we'll get lambda is equal to 3 and 1.
Yes. So lambda is equal to 3 and 1. So we have two values. As we have order of A is 2, so obviously we have two values here. Got it?
Yeah. I think there's one point that they've mentioned here. A has two real eigenvalues, each of them with multiplicity 1. What do they mean by multiplicity?
Where? Let me check it.
In the example,
Okay. So we have characteristic equation, this one. This is the characteristic, or you can say this is the characteristic equation. Or what do you want to ask?
there's a point
Eigenvalue.
here. So they've given us the spectrum, which would be 1 and 3. In addition to giving us the spectrum, they've added a line here. It just says A has two real eigenvalues, each of them with multiplicity 1.
Okay. Let me check it. What they are saying? Multiplicity one means GCD of both of them is one. Okay, and we have only real values here. Sorry, three. We have three. Sorry. Mm, okay, so multiplicity of them means GCD of 1 and 3. Obviously, we have one. Okay, and obviously, we have only real values. So, spectrum we can form uh, spectrum of A can be written as a having the whole eigenvalue which we have 1 and 3. Okay, so we have here two real values because we have only real values. Okay, and both of are real. Two values of lambda because we have two order square matrix. So each with multiplicity 1. You can consider it as GCD because GCD of both of them is 1.
Um, I'm sorry, ma'am. I have no idea what GCD is.
Pardon?
What is GCD?
Greatest common
Oh, okay, 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 okay.
divisor. Yeah.
All right, all right.
So now you got it?
Yes.
Okay. So let's see the next proposition when each eigenvalue lambda s and s here is equal to 1 to up to n are satisfy the infinitely many eigenvectors x to the power s and they are all known null solution of x. or we can write an linear homogeneous form. I'm telling you what it means by a homogeneous system of equation. And we can see the example further. Means when we find to find eigenvectors, just we multiply x to the characteristic equation.
Mhm.
Okay, let's do the example, shall we?
Yes.
I'm going to mention you to find eigenvectors, just multiply the characteristic equation by x. Multiply characteristic equation by capital X and put the value of lambda or eigenvalue, you can say, and find eigenvector. So now let us find and let us understand by using the below example. You got this thing? We need to multiply both side by using x characteristic equation.
Hmm. That's fine.
Okay, so just a second. Okay, I'm telling you one more thing. Uh, just a second. One thing is missing here. Characteristic or matrix, we can say, not characteristics matrix. What is it? I'm telling you, not by equation. Because we need to form matrix form also by putting a value of lambda. So let us take any value of lambda. Okay, we have this. Have we the same or we have different? Okay, we have the same value. Shall we use directly values of
Uh,
lambda?
yes, ma'am.
Because we are using the same matrix here. That is why. So let us take lambda is equal to 3. Now let us
Mhm.
put in this form, or simply we can write to find eigenvectors express the following matrices as, like we have a minus or lambda into I minus a, we have here. Now put the value of these all means lambda also. So we have 3 minus lambda, 3 is lambda, and a value of a we have here 3
Mhm.
and 2 0, and below we have, okay, 3 minus 1. So we have here 0 2 0 2. We have here minus lambda or lambda. Oops, just a second. Acha, no, okay, they are taking for lambda is equal to 1. Okay, all right. And we are doing here for lambda is equal
Yeah.
to 3.
3.
Okay.
Yeah.
And we are taking here x having, because this is of order 2 by 2, so we are taking two values here, x1 x2, and we'll take null matrix also on right side, and we can express them as ax or lambda into I minus a matrix can be multiplied by x and taking right side 0 as a null matrix. So here we have 0, 0, 2, and 2 here. And just multiply x1, x2 as and take right hand side null matrix, or you can say 0 matrix. So now let us multiply them in x1 plus, okay, just multiply them as, so 0 into x1 and 2 into x2 is equal to 0. And again 0 into x1 plus 2 into x2, 0. Okay, I'm just checking what they have done here. Minus. Okay, all right. My mistake. Just a second. Because we are subtracting them. So here we have 0 in this matrix. So here we'll get minus 2. Yes. Are you getting this point?
Yes, ma'am.
Okay. So how can we express now in form of eigenvectors? Because only its multiple is 0, but x1 not is 0 in itself. Are you getting this point? Are you getting this point?
Um, yeah.
Because in this expression, when we multiply with 0, then only we'll get 0 as small. Okay,
Hmm.
but x1 is not exactly 0. It has some values. So let us consider any value. Here they have given to us like beta. We can choose any value, okay, which is non-zero. Let x1 is equal to, you can take alpha, beta, a, b, any value. I'm going with your EDF. So we are taking, let us suppose x1 is beta 1. Why we are taking? Because of this 0. This term is 0, but not because of x1. That is why. So let us
Hmm.
consider this beta. And now we can express them, or by using this any one of them, because this entire term of 0, because of this 0, then we'll get this x2 also 0, by using this equation or by using this equation. Got it or not?
Yes, ma'am.
Okay, I'm telling you again.
So whenever
I'm
we're getting the 0, it's best to take
okay. I'm
um
telling you once again. See, we have, by on multiplying we have 0 into x1 minus 2 into x2 is equal to 0, and again 0 into x1 plus 2 x2 gives 0. Because see, 0 into x1 gives 0. Because if product of any two numbers, any one of them is 0, then result will be 0.
0.
Okay,
Yes.
but x1 is not 0 here. It has some other another value, okay, which is
Yeah.
not defined here. So we are considering here, let us take x1 is equal to beta. If we multiply this beta with the 0, obviously we'll get 0. So
Hmm.
here x2 will become 0. Are you getting this point?
Yes.
By using any one equation, are you getting this point? Suppose
Yes.
it has some values, okay, which is non-zero. and which is non-zero. So now let us put in any equation. In any equation you can put. Still, this entire term will become 0 and it has also 0. So after simplification, obviously we'll get x2 is equal to 0. Are you getting this point?
Yes, ma'am.
Yeah. So that is why here x2 is 0. Okay.
Hmm.
So x means eigenvector can be expressed as x is equal to having value x1, x2, and we can represent it as like we have considered this beta and this is 0. So we can take you can write in this form also, or can take beta as a common because another value means second value is 0. Okay, so you can write here 0 and 1 and 0 here. Okay, this is required eigenvector.
Okay.
Okay, you got it.
Yes, ma'am.
Okay, similarly you can find for lambda is equal to 1.
Yeah.
So here the remark, let us see this. If the set chi having the lambda s of the all solution included the null solution of x is equal to 0 also of this equation is called eigenspace of A associated with lambda s. Means me this chi, the symbol I'm telling you, just a second, this chi s of all solution. All solution means included a null solution also, mean having the zero means solution at 0 also, and included null solution of,
Uh,
yes,
I had a
of
question
this,
here.
yeah,
So how is chi lambda as how is this different from the spectrum?
sure. Means their spectrum we are using value of lambda. Okay,
Mm-hmm.
only eigenvalues. Okay,
Yeah.
and here we are finding for this means we are doing for the eigenvectors.
Okay.
Okay,
Okay.
yeah, this chi lambda is for eigenvectors and that s for eigenvalues only.
Oh, okay. So it's basically like the values of the basically the set of all the values of x.
Yes,
Okay.
exactly. Okay, so here we can represent this. We have lambda s into I minus a into x is equal to 0. So each eigenspace, uh, this I'm explaining you, each eigenspace, this chi lambda of sorry, chi lambda s, having s is equal to 1, 2, up to so on, is a linear space. Why it is, I'm telling you. Linear subspace, sorry, why we are saying them in a linear subspace of, okay, of subset of Rn. You know the symbol of subset from 1 to up to n is equal to 1 to up to,
Hmm.
or you can start from 1 to n. Means if we have a vector space from 1 to up to n, so this is any eigenspace is a linear subspace of that Rn. Okay. How? Because in Rn we have entire. Okay, we have entire value. Then subset of that entire is obviously subspace. Because this is vector space we are using this to represent this R. So you got the vector space already, because if you know the vector space only, then you can understand the subspace.
Um, I'll just read it once again.
Because to understand subspace or the topic that is subpart means a part of vector space. That is why I'm asking.
Hmm.
Sub,
Mm,
yeah, means vector space having the all vectors, all possible here. We are denoting by here Rn, and this is any this
okay,
chi
okay.
the lambda s is only one part of that. That is why we are
Yes.
saying this
Yeah.
subspace.
So, for example, if we had like a third value of lambda, and
Yeah.
whatever solutions we got from that, that would also be a linear subspace of R2.
Yes.
Okay.
Exactly.
Okay.
So you got it.
Yes, ma'am.
Okay. So let us see the next proposition. For every real matrix having n by n order, it is first part, we see lambda belongs to R. If and only if the symbol red represent the, you know very well, if and only if chi lambda is subset of Rn, means for every real matrix of order n by n, it is, we have first part, lambda belongs to R, means it will be obviously above meaning or above definition. Lambda belongs to R means this is real values uh, of lambda, and chi lambda is a subset of Rn. Are you getting this point? I'm
Yes.
just explaining you here also. If here we have real matrix, okay, and here lambda belongs to real number R, real number, okay,
Hmm.
then chi lambda will be the subset of Rn, because in Rn we have all, you know, in
Yeah.
Rn, because we have total n values, so we'll form the n vectors, set of vectors also. So this will be the subset of, obviously, because in Rn we have from 1 to up to n values, all entire values. In here we are finding any specific value that also belongs to the same vector, set of vectors. Are you getting this point?
Yes, ma'am.
Yes. Next point is, if lambda belongs to C over R, means having complex values also. C denotes complex.
Hmm.
Okay. If lambda belongs to C over R, then chi lambda also belongs to Cn over Rn. Complex eigenvalues, if and only if eigenvectors means if we have complex eigenvalues, for that we'll have complex eigenvectors. In simple words, you can understand that.
Mhm.
Got it?
Yes.
Yeah. So here we have x is equal to a plus iota b belongs to chi a plus iota b gives us x is equal to a minus iota b, which belongs to this chi lambda. Means if we have like mm, any value of a in a complex form, then we put in chi, or in you can say this in linear subspace. When we put the complex value of lambda, then we'll get obviously result in the form of complex.
Okay. Let's number. Yeah.
Yeah, this is the meaning.
All right.
For example, we can see here we have matrix A, and then obviously to find value of lambda, we'll find a determinant of lambda I minus A. Further, we'll form the characteristic equation,
Mm-hmm.
and obviously we'll have the values in pairwise, plus minus iota and root 2. So we have here values of lambda are imaginary, you can see.
Mm-hmm.
Now let us find the corresponding eigenvectors also. Is it okay if I'm doing with your PDF? Is it okay if you need the on whiteboard? Then I'll explain you. What do you say?
Um, ma'am, I didn't understand. Uh,
Okay. So shall we do the next topic?
yeah.
Okay, let me check. So do practice of all of these. Okay, let us do the next topic, which is next definition for every eigenvalue lambda s of a having order n by n. We have algebraic multiplicity of lambda s, that is equal to a into lambda s. The multiplicity of the solution characteristic equation. Okay, and geometric multiplicity. Let me check it. Okay, just a second. Do you know rank of matrix? You remember?
Yes. I remember very. I would prefer to like revise it once.
Okay, okay, all right. I'm going to remember you. So, what is the rank of matrix? Like if we have 3 by 3 order matrix, A1, B1, C1, A2, B2, C2, and A3, B3, C3. We always find a rank of square matrix for which we can find a determinant. So obviously we can find determinant for only square matrix. So if we have determinant of A, not equal to 0 for this case, then we can say its rank is 3. If at any order, if its determinant is non-zero, then we can say the given order is the rank of the matrix. Got it? And in another case, if determinant of A is equal to 0, then by
Mhm.
using elementary row or column operation, we'll
Okay.
reduce this matrix into 2 by 2. Okay,
Mhm.
then after
Mhm.
that we'll find the determinant of that 2 by 2, then check that if its determinant is non-zero, then we can say its rank is 2. Otherwise, if still for 2 by 2 its rank is, oh sorry, its determinant is still 0, then we can say its rank is 1 only.
Its
Are you getting this
rank
point?
is
Its rank is 1 only if
okay.
means, for example, if we have determinant of this matrix is non-zero, okay,
Mhm.
then we can say its rank is 3.
3.
Okay, in this case when it is non-zero. If it is 0, then we'll reduce this entire matrix into 2 by 2 by using elementary row or column operation.
Yeah.
Okay, then
Yes.
after reducing into 2 by 2 order, then we'll find again determinant of that 2 by 2. If still get you have determinant of that 2 by 2 0, then you can say for 2 by 2 it also 0, so you can say its rank is 1 only. If it
Mhm.
is non-zero for 2 by 2, then you can say its rank is 2.
Okay.
Shall we do one example for that?
Yeah.
Okay, it will take time. So, can we do tomorrow? Oh, sorry, day
Yes,
after
ma'am.
tomorrow when we have next class?
Ma'am, we can do on Friday.
Sure, sure. On Friday we'll do.
All right.
Okay, so first of all, I'll log in your class at sharp 4 p.m. So we'll start then.
All
Okay.
right. Thank you, ma'am.